Sometimes knowing the dimension of a vector space makes it easier to find a basis of that space. To explain why, first I'm going to need another fact about linearly dependent subsets of a vector space. I'm going to call this fact a lemma. Roughly, lemma means something that doesn't look very useful at first, but then you're going to end up using it later. So this lemma says that let's let T be a collection of m vectors, and let that be a linearly dependent set. In a vector space V. Then I claim that there is some subset S inside of T which is linearly independent and has the same span. So span of S equals span of T, even though S is only some of the vectors that are in T. So we can throw away some vectors and still have a set that has the same span as the first one. So to see this, recall that in a linearly dependent set, we can always find one vector which can be expressed in terms of the other vectors. It can be expressed as a linear combination of the other vectors. So remove it. So remove it from T to obtain an m-1 element set, because T had m elements. So we'll take it out. We have an m-1 element set. Let's call it T prime, with span of T prime equals span of T. Now the span is equal because since this element that we just removed is a linear combination of the other elements, then if we look at all possible linear combinations of the other elements, there isn't any one of them that we actually need this removed element for, because by itself it can be expressed as a linear combination of the other elements. So we don't need it. We remove it from T, we've got an m-1 element set, T prime, with the same span. If T prime is linearly independent, then we can stop. Otherwise, we can repeat this process, taking out vectors that we don't need because they can be expressed as linear combinations of the other vectors. And we can repeat the process until we have a linearly independent subset S with the span of S equals the span of T. So whenever we have a linearly dependent set, we can always take out some vectors and get another set with the same span as what we started with. And we can do that in such a way that the set of vectors we're left with is linearly independent. All right, now let me tell you how knowing dimension makes it easier to find a basis of a vector space. So recall that a basis of a vector space is a spanning set of that vector space that is linearly independent. Spanning the vector space means that you can take linear combinations of this set to get anything you want in the vector space. Linearly independent means the only linear combination of these elements that's equal to 0 is the zero linear combination. So those two properties, being a spanning set and being linearly independent, define basis. That's what basis means. All right, now I claim that if the dimension of a vector space V is n, then any n element linearly independent set is a basis. So that is, it's automatically a spanning set, just because it has the right number of elements and it's linearly independent. Well, I didn't name my linearly independent set. So let's let V1 through Vn be a linearly independent set. And let's choose some other vector W. So let's choose W in the vector space. And I'm trying to show that this linearly independent set actually spans V just because it has the same number of elements as a dimension of V. So I'm going to try and show that W has to be equal to a linear combination of these. That'll show that any element in the space can be expressed in terms of these, and therefore that these span the space. So let's choose W, and we claim that W belongs to the span of V1 through Vn. So to see this, observe that if we add W to that set, then we're going to have n plus 1 elements in an n-dimensional vector space. So that's definitely going to have to be linearly dependent. Because whenever you have more elements than the dimension of the space, it has to be linearly dependent. So observe that the set W v1 through vn is linearly dependent. And that's because it just has too many elements to be linearly independent. So that means we can write C naught W plus C1 V1 plus dot 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 Cn Vn equals 0. So it's a linear combination of W and all the V elements. If the set is linearly dependent, then that means that we can write this equation with the C's not all being 0. So with C naught, C1, etc. up to Cn, not all 0. Now actually we can see right away that C naught is not 0. In fact, C naught is not 0. Because if it was one of the other coefficients that's non-zero, then we would have a linear combination of v1 through vn with the coefficients not all 0 that's equal to 0. But v1 through vn is supposed to be a linearly independent set, meaning we can't do that. So C naught is not 0 because then we would have C1 V1 plus dot 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 Cn Vn equals 0 with coefficients not all 0. This is impossible since V1 through Vn is a linearly independent set. Alright, now if C naught is not 0, then we can take this equation, put all the v's on the other side, and write W equals, let's see, negative C1 V1 is going to be on the other side. Negative C1 divided by C naught if I want to make W be all by itself. So I'll subtract all of these from both sides and divide by C naught. So W is minus C1 over C naught V1 minus C2 over C naught V2, etc. minus Cn over C naught Vn. But there we have it. So I wanted to show that W is in the span of V1 through Vn, meaning W is some linear combination of these. It is. W is this linear combination of V1 through Vn. So W does belong to the span of V1 through Vn. And since W is just some arbitrarily chosen vector in the vector space, that means that any element we might choose belongs to the span of those. In other words, these do span the whole space. So the span of V1 through Vn equals the whole vector space V. So again, if we know the dimension of the vector space is n, and we have a linearly independent set that has exactly n elements in it, it automatically spans the space, so it's automatically a basis. Now the next thing I want to claim is that suppose we have a dimension space, we have a vector space of dimension n. So if dimension of V equals n, and I'm going to say then any spanning set v1 through vn of exactly n vectors is a basis. That is, it's automatically linearly independent. So let's suppose we've got a spanning set. So suppose the span of v1 through vn equals the whole space V. I want to show that this is linearly independent. If it's dependent, so if v1 through vn is linearly dependent, then the lemma, so here's where we're going to use the lemma, which maybe didn't look useful before, but now we're going to use it. So then the lemma implies that it contains some smaller subset inside of it that has the same span and is linearly independent. So there is a subset of v1 through vn that is linearly independent and has the same span. But if it's linearly independent and has the same span, which is the whole space V, then I guess it's a basis. So this subset must be a basis. Because it spans V and it's linearly independent. But that's impossible because we said in the last video that every basis has the same number of elements, the dimension of the vector space. So we would have just found a basis with fewer elements than the dimension of the space. That's impossible. So this is impossible. Since no basis of an n-dimensional space has fewer than n elements. So if that's impossible, then we trace back to what were we assuming We assumed if this is linearly dependent. So that can't happen because it leads to something impossible. So that means that the set must be linearly independent. So V1 through Vn is linearly independent. And if it's linearly independent and spans the space, then it's a basis. So again, the important two results to remember, the two results that are more important than the lemma, are that if we know the dimension of the space is n, then any spanning set of size n has to be a basis, and any linearly independent set of size n has to be a basis. So knowing the dimension is n gets us off the hook for having to check two properties. We don't need to check that something is both a spanning set and linearly independent. Knowing that the dimension is n and the number of vectors we're looking at is n, it would suffice to show either that it's a spanning set or linearly independent. After showing just one of those properties, we can conclude that it's a basis. The end.